Okay, thanks for having me. So I'm going to talk about some work that I've done on a phenomenon called stochastic pumping, which I'll get into at the beginning. But I would like to use it because this is a workshop setting to try to motivate some more formal questions in large deviations, specifically for systems that have some sort of time periodic driving. So I suspect many of you are familiar with this idea that's known as the stochastic pumping phenomenon. Basically, the idea here is that you can generate a current through a system in two different ways. You can have some sort of steady state where you're driving a system with a perturbation that is invariant in time, or you have some sort of gradient through the system that is causing flow of material or flow of energy in some way that's generating a current. Alternatively, you can perturb the system in time to generate currents. So this is sort of the simplest schematic example of what a stochastic pump might look like. You could have a set of energy levels and barriers between them. And by periodically varying the energy levels and barrier heights, you can drive the system out of equilibrium and generate a non-zero average current. What is sort of perhaps non-intuitive about this is the fact that at any fixed time, the rates may satisfy detailed balance. So you can have, say, Arrhenius type rates connecting each of these transitions. And if I were to stop the clock, fixed time, the system would relax to a Boltzmann distribution. It would occupy equilibrium statistics at each of these energy levels because these rates are detailed balanced. But by driving it at a finite rate, the system falls out of equilibrium, and as a result, you have probability being pumped through this network. This is not a new idea by any means. There's actually quite a rich literature characterizing stochastic pumps at the level of averages. So some of the results worth highlighting are ideas called the no pumping theorems, which say basically if I have any sort of network of the type that I drew on the previous page, in order to generate a current, you need to modulate in time at least one energy level and one barrier height. So I need to be modulating this in time and a barrier height in time. If I only modulate the energy levels or only modulate the barriers, then you cannot generate a current through the system. So there are nice proofs of this result due to Nikolai Soninson and Dibya Numandal in different types of settings. There's another aspect of this which is quite interesting and relates the idea of pumping to a Berry phase in quantum mechanics, so geometric pumping. So you can describe the dissipation with a geometric factor. So, however, far less is known about the fluctuations and yeah. Go ahead. Any question? Oh, okay. So the idea here is a really schematic one, but it's taken from reaction rate theory. So the idea is that you have maybe some free energy landscape or energy landscape, and you're defining the states in this Markov network as the different energy levels that you're occupying. And between those energy levels, there may be some barrier in the free energy that you have to overcome in order to transition from one to the other. So there's a procedure by which we assign a reaction rate, so say K, 1 to 2, right? Which in the simplest setup is something that looks like what's called an Arrhenius rate. So you have a barrier separating the two, which is of height B. And if you're initially in, say, E1, then that determines the rate. So it's a way of assigning rates to some sort of schematic picture that's taken from a free energetic perspective. But you could set up these rates in any sort of way that could be physically motivated by the setting that you're describing. So you by no means need to be using that formalism in order to describe what the rates are. Right? You can just think of them as rates. Okay, so the topic that I want to focus on is not the average level of these stochastic pumps, but rather their fluctuations. So I want to start with just a fairly straightforward calculation of what a large deviation function might look like for a deviation away from a periodic steady state. Okay, so in this setting, what I want to do is just compute a scaled cumulant generating function for the total entropy production in my system. And yeah, I think after Ugo's lectures, we should all be quite familiar with what these scaled cumulant generating functions mean and are, and how we define them. And the important thing here will become the periodicity. So the most straightforward way of computing this average that I've written in the first line would just be to start with an arbitrary initial distribution. So it doesn't matter what it is, because you're going to forget about it, and just integrate it forward in time and just compute this average explicitly, right? So that's all that this equality is doing. It's saying, I have this average, I have one way of computing it by using a tilted generator for the entropy production, and I can just do an ergodic average, right? Just run this for a long time and compute that average. Okay. So in principle, that's something that you could do on a computer, right? You could numerically solve this equation and try to get out an estimate for psi of lambda. But in this periodic setting, we can do a bit more by using the periodic steady state. So because this dynamics is going to conserve probability, we'll end up with a distribution that relaxes to a periodic steady state. And so I can take this ergodic average and I can rewrite it instead as an average over cycles through my system, right? So I'm just going to sum up, okay, so in tau is now t, right? It's the number of cycles times the period of an individual cycle. And I can sum all of those up and compute this deviation at the level of each period. Okay, so rather than just looking at one extremely long trajectory, what I'm doing is I'm treating all of these independent periods as independent periods, and I'm just adding up the deviations within those periods and saying that that's the dominant thing. And because this is going to relax to a periodic steady state, each one of these independent cycles should contribute the same. And I can eliminate that in and just compute this as an integral over a single period. So this formula, which I have been using, I haven't found elsewhere in the literature, and I'm not sure what exactly the assumptions that are necessary to make this a rigorous statement. In fact, I would take a step back and even say that I'm not sure what is necessary to prove the existence of an LDP for these sorts of periodically driven systems. So as soon as you have these dependent dynamical phenomena, the time-dependent rate matrices, the spectral methods become much more complicated to use because you have to deal with the problem of time ordering, which is something I'll get into towards the end of this talk. So this is just meant to sort of elicit further discussion while we're here, and maybe this is something that someone has ideas about. Okay. So one approach that you could take to sort of dealing with these time-dependent phenomena is to attempt a sort of coarse-graining. So maybe I can't do all of the analysis that I would like to do on a time-driven system, but maybe I can coarse-grain it to a non-equilibrium steady state in a way that allows me to use some of the more powerful tools that we have in that setting. There have been a few ideas about how to do this. I think the first is probably Roisia and Schmidtman in 2007, who established what they called a dynamical equivalence principle. And the basic idea of this principle is that the two ingredients that are necessary to characterize a stochastic process are the currents and the steady state probabilities at each site. So in some sort of Markov process, right, on a graph, as I've written it, you would have occupation statistics of every site on your network and the currents between those sites. Okay, and so they use a decomposition of the steady state rate matrix that puts the weights of each site, the occupation statistics, on the diagonal, and separates the rest of the matrix into a symmetric and an anti-symmetric part. So the anti-symmetric part is uniquely determined once you know the currents. Okay, so the basic procedure here is actually one that is maybe not so straightforward to use, depending on what the problem is. But what you would need to do is, compute. So if I have some stochastic pump or some time dependent driving, what I would need to do in order to use this sort of formalism is I would first need to compute the currents periodically averaged along each edge in my network, and I would also need to compute the steady state occupation statistics in order to construct my matrices P and A. Okay. So that problem could be prohibitive in various settings, right? But let's assume that we can at least get that far. We can compute these quantities that we need in order to construct the steady state rate matrix. So that specifies one part of my rate matrix, but I still have this symmetric part that is unconstrained. And that lack of a constraint leads you to the question of how you should choose it. So Oren Raz and Chris Czerzinski wrote a paper where they looked at this coarse-graining, and they said, well, one way of introducing a constraint is just to match the average entropy production along each edge of my network. Okay, so again, now in order to use this formalism, right, so then you would also need to compute the periodic average of the entropy production along each edge. But if you can compute the currents and the densities, you can probably do that too. So this will guarantee that on average, the coarse-grained representation of my stochastic pump will match the current, the average current, the average occupation statistics, and the average entropy production. It makes no guarantees about the fluctuations, however. So let's just take a look at what those fluctuations do for a simple example. Okay, so I've constructed a very schematic and simple system here. Right, so I have 4 different states which have energy levels, only one of which is being varied in time, and one barrier height that's being varied in time. And the rest are just static with all of the energy levels at 0 and all of the barrier heights at 1. Okay. And for this, I can compute the periodic steady state, which is shown as these curves in different colors for each of the sites. And then the periodic averages of those the steady state occupation statistics are shown as dashed lines. Okay. So, there are substantial oscillations in the probability of occupying the site through the period, but they are periodic, of course. Okay. So at the level of currents, the occupation or the fluctuations are quite different between the two representations. So you'll notice that this is at the level of the rate function, meaning that these deviations that we see are exponential in scale. These are very substantial deviations in the fluctuations between this representation under the coarse-graining and the stochastic pump. Similarly, for the same cycle, we find that the fluctuations in the entropy production are similarly dramatic. Right? Basically, the fluctuation spectrum is completely wrong between these two different representations of the process. So I want to take a quick diversion to motivate us. Yeah. Yeah, so the space is exactly the same. The only coarse-graining is a coarse-graining in time, basically. So I'm just saying I'm going to take this time-dependent rate matrix, and I'm going to try to represent it by a rate matrix that has time-independent rates. So the difference, of course, will be that the time-independent representation has to break detailed balance, where the time-dependent representation at any fixed time has detailed balance. So they're different rate matrices with different propagators. But okay, so I want to make a quick diversion to try to motivate a different perspective on how this coarse graining might be viewed. And I don't know if Ugo talked about level 2.5 large deviations at all. So I think we'll hear about this in gory detail probably from Todd. But I just want to introduce basically what the ingredients are to level 2.5 large deviations. So just a historical note on the name, I guess. It emerged from the level formalism in large deviations, where level 2 is the large deviation function for the empirical density. Level 3 is a large deviation function for an empirical process. And this sits somewhere in between, so they decided to call it level 2.5. But the function has two ingredients, one of which is just an empirical density. So at each site, this is just, for a trajectory, it's the average occupation statistics. That's why it's empirical. And the empirical flow, which is written in a fairly non-mathematical way as an integral over jumps, basically, in my Markov process. So for each edge in my system, I'm basically counting up the number of hops in a directed fashion. So I want to make a quick point about the difference between flows and currents. So the flow, so let's just take a single edge. The flow along this edge in the forward direction is the net number of hops per unit time. So the flow Q from A to B is number of hops per time. Right? And the same goes for the reverse direction. The current, of course, contains information about both directions, right? So the current will be number of forward hops minus the number of reverse hops. Over time. Okay, so I think it should be very clear that the flow contains substantially more information than the current. So for example, I could have a flow in one direction of 100 hops and in the other direction of 80 hops, and that would give me a current of 20 hops per unit time. Whereas the types of different fluctuations that you could have with a current of 20 is much less constrained, right? A current of 20 could mean that I'm in that situation where I have 100 forward hops and 80 reverse hops, but it could also mean that I have 20 forward hops and 0 reverse hops. And obviously, those are somewhat different processes, and will of course lead to different fluctuations. But this level 2.5 function is given in terms of flows, and from this expression, which is exact and is known for conservative currents, we can get any spectrum of fluctuations in any current that we want via contraction. This idea of contraction plays an important role in the uncertainty relations. Baratta and Seifert and Todd has worked on quite a bit. And they motivate questions about many more systems than the sorts of steady states that they were initially proved for, one of which is going to be partially resolved in this talk, which is whether or not such a bound holds for periodic driving. I'll describe these uncertainty relations in a little more detail later on. And whether or not there is a level 2.5 function that we can write down in a coherent way for these periodically driven systems. Okay, so based on that idea of level 2.5 well characterizing a dynamical process, we should take a step back and reconsider how we chose this symmetric part of my rate matrix S. So here we left it unconstrained initially and then chose it to match the average entropy production. But the idea of level 2.5 says that instead you shouldn't worry about matching these average currents with the asymmetric part. What you should do is just try to match the flows. In a way, this is the most obvious thing to do from the get-go, right? It's saying that if you want to choose the rates on your rate matrix optimally, what you should do is choose them to be the directed periodic averages, right? So basically, if I were able to measure this forward rate in my periodic system, then I would just choose the average rate as the rate for my rate matrix. So instead of choosing J in this, or choosing A and S in this way, what I'm going to do is just choose them both so that I match the flows on average. So then I will get the right currents. And let's just take a look at what that does for the rate functions. So what we find is that when we choose the symmetric part so that we recover the flows out to very large scales, we match the fluctuations in current pretty precisely. You can see a small deviation out in the wings. This is something that I'll describe a bit towards the end about the breakdown of this equivalence. But it clearly is doing a much better job and is much more faithful to the representation of the underlying process. However, when we look at the entropy production, what we find is something that's quite different again. And here, the fluctuations, the agreement with the fluctuations is perhaps even more degraded than it was in the first example. So we have to ask the question of whether or not this is a problem. Well, so I would argue that it's not a problem, and this is the rationale for that argument. So the stochastic pump has an entropy production that is defined, in terms of these time-dependent rates, but we can split that contribution into two different parts. So the first part you might call a cycle contribution. That's the entropy production that comes from the cycles through the network. The second part of this contribution is something that we might call the excess or dissipated work. So when I do these sorts of manipulations to a system, right, I'm pumping energy into the system in order to generate a current. Some of that work that I do on the system is getting translated into a current that we measure and resolve as dissipation through these cycles through the system. However, some of that work that I do is just being dissipated as heat to the back. Right? It's not perfectly translated into current, except in the adiabatic limit. So this sort of decomposition can be formalized easily, and what you'll find is that this contribution to the entropy production is strictly positive. It's really like a measurable physical entropy production, as is this one. So that decomposition suggests that you shouldn't expect the stochastic pump entropy production to match the entropy production of the steady state representation, because they really are sort of physically different measures. Okay. So I want to sort of make an additional justification of why this approach to choosing the rate matrix is the correct one, which is basically to say that if you do a Fourier decomposition of the master equation in this periodic steady state, what you'll find is that the first order term gives you the steady state representation that we've already chosen. And I want to emphasize that this is distinct from a time-ordered exponential representation of the periodic propagator. So sometimes people will call this thing the stroboscopic generator. So it's not as though I've just chosen the Markov representation for the whole period. This coarse-graining is different and is resolving information about what's happening inside the period, which is an important part of getting those fluctuations right in the first place. Okay, so the consequence of all of this for the uncertainty relations is pretty direct. So in this weakly perturbed limit, where I take just the first Fourier component of my rate matrix, I can prove an uncertainty relation for the stochastic pump of the type that Barato and Seifert and Todd Gingrich and Jordan Horowitz have worked on. Which is to say that for any current that I consider through my system, the rate function of the stochastic pump for that current will be bounded by a quadratic in J, with a variance associated with the Gaussian that quadratic represents, that's determined not by the total entropy production, but by the steady state entropy production. And this is actually a good thing, because the steady state entropy production is strictly smaller than the stochastic pump entropy production. So in a sense, that's saying that the bound is tighter. As you can see here, it may not be that important. I've plotted the bounding function on the scale, and the bound is quite weak for the example that I've considered here. But it has consequences that may be relevant in some cases. So I wanted to make a quick comment about some very recent work of Karel Prosmans and Christian Vandenbroek, where they've shown that a distinct bound exists for time-symmetric driving, and this bound is not the same as the uncertainty bounds, but has a sort of similar spirit and relies on a large deviation function for the flows that has the following expression. This I find a little non-intuitive, but it's fairly heuristic in the way that they've written it. It's a sum over periodic trajectories, so all trajectories within the period gamma of the flow within that period, and then this is sort of the static part of that. I'm not sure that this expression can be proved rigorously. But it's something, again, that I would like to discuss here with anyone who's interested. So I think I'll probably conclude with that, and just thank ICTS and the organizers for having me, and funding. And a lot of this work was carried out while I was at Berkeley, but I've now moved to the Quran Institute at NYU. All right. Thanks.
I think I missed a detail when you for the estimation of those that time integrated operator. Do you only look for do you only take the same transitions as the microscopic ones, or do you also put something in for the transitions that don't exist at
the transitions that don't exist?
Well, like in your model, there's two states that were not linked directly by a transition, which would have an entry in the stroboscopic matrix, right?
So the graph is fully connected.
It was?
Yeah.
No, 2 and 4 are not connected.
Oh, you mean, okay. So yeah, not directly connected. So the question is then,
like, well, do you look for an effective position between 2 and 4 as well, or not?
No. So those rates are just kept as okay. 0, right? So only the transitions, all the state space and all of the edges are kept invariant through the coarse-graining.
Okay. So it's quite different from the stroboscopic operator. Because it would have an entry on that. Will be fully connected.
I mean, you could.
No, I think it always is. If you're ergodic, the stroboscopic one is always full.
Yeah. So the perspective here is very much divorced from that, right? I mean, you can derive those, and will get a Markov process, right, that takes you from one period to the next. But the point is just that the fluctuations within the period are the sort of important thing for the large deviations, rather than the fluctuations from period to period.
Yeah.
So
Right.
Yeah, so the stroboscopic perspective is not something that I really use. I just wanted to make sure that
No, but
this is divorced from
that's
that.
even clearer if you don't have that transition. But you would have, on a period, you would have fluxes from 2 to 4.
Yes. Yeah.
Which end up not being important apparently for the currents, or I mean, how?
Well, so those fluxes can still arise in the steady state, right? It just requires two transitions.
Yes. Okay. All right. Yeah. Right, thank you.
Questions? I would have a question. Can you go to the plot where you show actually the one that sits on the rate function of the stochastic pump?
Yeah. This one.
Are all the red dots actually a process in which you change the flows, but for each of the fluctuation, or that's actually a process which is fixed?
So that process is fixed. I'm computing it for a different. So I mean, I construct a cumulant generating function, right?
That's where
do a Legendre transform, but yeah, it's a fixed rate matrix.
But do you think you can always find a process where you fix the flows that will actually sit on top of the rate function for the periodically driven system? Or
so you're saying if I were to demand that I have a current of -4 or something, could I find a rate matrix?
No. I mean, here it seems that for that particular model, you can find one that's steady state with the same fluctuation.
Yeah.
But can you always do that by fixing the flows instead of fixing the current?
So you can't always do that, and so this is something that is discussed a little in the supplement of my paper. So you can degrade this agreement between the rate functions by having very dramatic changes in the occupation statistics, for example. So you'll always get the area near the quadratic part of the rate function pretty well, but as you go out to the tails, you can have the agreement degrade quite a bit. Yeah. So basically, from this Fourier decomposition perspective, if the higher modes play a really important role in describing the evolution of the periodic steady state, then you can lose that agreement. Mm-hmm.
And then related to that also, when you looked only at the steady state system where you fixed the current, the rate function was on top of the rate function for the periodically driven system. Is that something general too, that you'll have only an upper bound on the rate function for the periodic system? Or?
So yeah.
For when you fix the flow, the rate function seems to be a bit under, but at least for those where you fix the current, it's sitting on top.
That I think is going to be general, and I think it's going to be related to the fact that you have so much excess entropy production. I think you can show that. I haven't tried to show it carefully, but it's definitely something that I think is true. Yeah.
Okay. Questions? Other questions? If not, then let's thank Grant.